We're looking here at Shigley's example 7-1. At a machined shaft shoulder, the small diameter D is 28 millimeters. The large diameter D is 42 millimeters, and the fillet radius is 2.8 millimeters. The bending moment is 142.4 Newton meters, and the steady torsion moment is 124.3 Newton meters. The heat-treated shaft has an ultimate strength of 735 megapascals and a yield strength of 574 megapascals, and the reliability goal is 0.99. Firstly, determine the fatigue factor of safety. Using each of the fatigue failure criteria described in this section, we are just going to focus on the DE, which means von Mises, Goodman criteria. Now it's good to know what we're looking for before we start the problem. So if we look back at the Goodman criteria in combination with the von Mises stress, what we see is that for static failure with no stress concentration, you have the von Mises as 16 over pi d cubed square root of 4 m squared plus 3 t squared. Put that into the Goodman criteria for failure. Combine those two, where we have the Goodman is 1 over n equals the alternating stress over the endurance limit stress plus the mean stress over the ultimate tensile stress. Combine those two and we get this equation where we have to incorporate the stress concentration, Kf and Kfs. So we have here the stress concentration Kf times the alternating bending moment plus 3 times the stress concentration in shear times the alternating torque. However, for a beam problem, we don't have any alternating torque. It's not going back and forth. We do have alternating moment because the point that we're interested in, for example, these letters, is flipping from top to bottom. So it's flipping from compression to tension, back and forth. So we don't have any alternating torque, so we can get rid of this term. We also don't have any constant moment because the bending moment is entirely compression, then entirely tension. So we can get rid of this term. And so we have what's left over is an alternating bending moment, so an alternating bending stress, and an a constant torque because there's a gear here and there's a gear here, and that torque, because it keeps going the same direction, it stays constant between the two. So this is the equation that we get and that we have to fill out then here. So this tells us what we need to go find. We already have the diameter. Which diameter is going to be the worst scenario? It's going to be the small one. So that's our D. And then this is our big diameter. So that's going to be our diameter, the 28 millimeters in there. And then we have 2 times the stress concentration factor. We're going to have to go find that. And the alternating moment over the endurance limit, we'll have to find that. Okay, so what's going to go into this endurance limit is going to be the SE prime that we have to find, and the Marin factors, all those Ka, Kb, etc. We already have the SUT. It's up here, 735. We're going to have to find the KFS using the data in the book, and we already have both the M, that's alternating M, that's our alternating M, and the TM. So we got those. So the things we have to find are the KF, the KFS, and the SE. So let's go get them. First off, the KF equals 1 plus Q times KT minus 1. Okay, so what is Q and what is KT? Q is the notch sensitivity and KT is the stress concentration factor. So there's a plot that we have to go use to identify both the Q and the KT. First off, the KT. To find the KT, we have to use figure A15-9. In this figure 15-9, along the horizontal axis, we need R over D. What was our radius? We look back at the problem. The radius was 2.8 millimeters. We have 2.8, and the little diameter is 28 millimeters. 2.8 over 28 equals 0.1. So we know we're starting here. We're going up, but where are we going? D over D, our big diameter is 42. The little diameter is 28. So 42 over 28, and that equals, so we got our KTS of 1.42 from the stress concentration factors. This is the shear, so that's KTS, S stands for shear. Our R over D ratio, radius of 2.8 millimeters over 28 millimeters is still 0.1. we go up to between d over d equals 2 and d over d of 1.33 should be 1.5, somewhere in there. And we come across to read our KTS off of here, and it is read as 1.42. And then for the stress concentration factor in shear, it's different from tension. So we have to go to our stress concentration factor in shear, figure 6.21. Our notch radius is still 0.11 inches. Again, that's 28 millimeters converted to inches. We go up to our strength, which is 735 megapascals, so it's a little bit above 0.7 gigapascals. Takes us up to about a little bit above this line, brings us over to just above 0.9. And so that's interpreted as 0.92, which gives us a value of 1.39 for KF and KTS. So now we go back up here to our equation. We've got the KF, we've got the KFS. KF and KFS is done. Got the MA, we got the TM. Now we need to get the endurance limit. So first we need to get the endurance limit that's before we multiply by all the Marin factors. That would be S sub E prime. Remember that the endurance limit, the equation comes from these data, where the endurance limit is about 0.5 times the ultimate tensile strength, until you get to an ultimate tensile strength of about 1,400. So here's our equation, 0.5 times SUT. So the endurance limit is half of the ultimate tensile strength for SUT less than 1,400, and then it stays at 700 for any SUT ultimate tensile strength over 1,400. So in our case, it's 0.5 times 735, which equals 367.5. Now we need to calculate all of our Marin factors. First Marin factor, K sub A, is the surface factor. And we look at the equation for surface factor is Ka equals A times SUT to the B. Let's get that equation and then see where those come from. A SUT to the B power. Okay, so we know SUT is 735. So we need a coefficient and a B power. For the surface factor, those values come from a table based on empirical data. In our problem, we said that the material is, I believe, machined. We have to go back and look. And so you have the prefixes or the coefficients in KSI and megapascals. Our problem's in megapascals. So for machined, those would be, I don't remember if it's machined or ground, but we'll look back and write it down. 1.58 and 4.51, and the exponent is negative 0.085 or negative 0.265. It says machined. So the value we need for megapascals is 4.51 times 735 to the negative 0.25. And the result is 0.787. And the second Marin factor, K sub B, is the size factor. In millimeters, the size factor is 1.24 d to the negative 0.107. For diameters, 2.79 is less than diameter, is less than 51 millimeters. And then 1.51 d to the negative 0.157 for diameters 51 is less than d is less than 254 millimeters. Our diameter was, if I recall correctly, 28 millimeters. So we'll choose this equation, plug that in. For d equals 28, the answer is the result is 0.870. Now K sub C is the load factor, and all of our fatigue is coming from bending. So for K sub C bending, the factor equals 1. If it was axial fatigue going back and forth, okay, with the tension, then that would be 0.85. If the torsion was going back and forth, it would be 0.59. But ours is bending fatigue because this is rotating. So K sub C equals 1. K sub D is temperature factor. We're at room temperature, so the K sub D equals 1. K sub E is the reliability factor. We have a handy-dandy table for reliability factors. We can go to this table. We'll go sideways here. Okay, for a reliability of 99, across here, the transformation variable is Z of Z is 2.336. We don't need that because we can just go straight to the reliability of 99. 0.814. So reliability for 99% reliability from the reliability table, 0.814. And then fortunately, in this case, we have no miscellaneous. So these are all our Marion factors. We use our Marion factors to multiply by the S sub E prime. Which ones had a value other than 1? We had Ka, Kb, Kc, Kd is 1, Ke. So that is 367.5 times 0.77 times 0.870 times 0.814. So the result for SE is 205 megapascals. Now we have everything we need to plug in here. We have the Kf of 1.58. Again, this is our von Mises or DE Goodman. So von Mises, and then our fatigue failure criteria is Goodman. The 1.58, the MA is 142.4. I'll rewrite this. The SE, now we have that value, 205. We're just checking here to make sure we have everything. 1.39, then SUT, so we're good. So let's rewrite this so we can do the math. So here's our final equation. 1 over n equals 16 over pi, 28 millimeters cubed, it's a cube there, times this whole quantity, 2 times 1.58 times 142.4 over 205, plus the square root of 1.39 times 124.3 over the ultimate tensile strength of 735. Solve this for n, and you get n equals 1.62. One important point to make here, though, is that you don't have to plug everything into the equation all at once. You could just solve for the alternating stress and the mean stress individually, where the alternating stress would then equal, according to the von Mises criteria, 32 times Kf times the MA over pi d cubed. If you plug those values in, 32 times 1.58 times the 142.4 over pi times 28 millimeters cubed, and you get 104.4 megapascals. Gotta watch your units, but alternating stress of 104.4 megapascals. And then the mean stress is based on the torque. So to calculate the mean stress, square root of 3 times 16 times the KFS times the torque, again divided by pi d cubed. That's square root of 3 times 16 times 1.39 times 124.3 over pi times 28 cubed, and that equals 69.4 megapascals. Then we can take those two values and we could plug them into any of the criteria for fatigue failure. So the one that we just plugged it into was the Goodman, where 1 over n equals alternating, so that's a straight line. The Goodman is a straight line between the endurance limit and the ultimate tensile strength. Or for example, the ASME criteria, where 1 over n squared equals sigma A over the endurance limit. So the alternating stress over the endurance limit plus sigma M over, instead of the yield strength, or instead of the ultimate tensile strength, the yield strength squared. So if we used this ASME equation and plugged the values in, we were given the yield strength in the problem of 574. So here I get a value of 0.73. So I need n equals square root of 1 over 0.273, and I get n equals 1.91. So the Goodman safety factor appears to be lower, somehow more conservative than the ASME safety factor. Goodman 1.62, ASME 1.91.